Thank you. So my name is Lisa. I am a data scientist at the Rubicon project on the Buyer Cloud. So at Rubicon project, we are in the business of automating advertising. We've already heard from an advertising technology company today. The Rubicon project is also a advertising technology company. Specifically at the Buyer Cloud, what we do is we work with advertisers to help them target the advertising to the right audience online and through mobile channels. So we slowly moved to Spark over maybe more than a year and a half ago, and it's been a great ride since then. Because as you can imagine, we have tons and tons of data, and we do tons and tons of calculations on that. And so today we are, I am going to present a problem to you that we leveraged Spark, GraphX, and specifically Pregel in order to solve. And this problem has to do with identifying new customers for our advertisers. We typically do this using intent data that we purchase through our data partners. And the one that we're going to focus on today is browsing history. So there's a stick figure there. We'll call him Bob. And we're going to say that he visited these two websites. So can we use this information to help decide whether he's going to be interested in any of our advertisers? So this problem has several challenges associated with it. Other than there being tons and tons of users, sites tend to be very numerous. There's a very high dimensionality associated with it. And there's also a long tail phenomena where a few users will visit lots of the common sites, and then there's going to be a long tail of sites where there's a lot of sparsity. And also sites tend to change over time. We don't visit older sites anymore, and newer sites come up every day. So there's an issue of sites being ever-changing as well. We also not only need to build one model, but we're actually building one model for each of our advertisers. So that also puts a constraint on the complexity of the model that we could build. So the third one on there is positive training cases. So the positive training data come from known converters. So people that we know had converted for a particular advertiser. And compared to just all users, that tends to be much sparser. And lastly, we evaluate users very frequently. We do that every few hours. So every user gets evaluated against every advertiser every several hours. So that, again, puts a constraint on the type of computation that we can do. So that being said, we do have our positive and negative labels, and we do have our training set now. And we also have a fairly natural offline evaluation metric. So the two that we use, they tend to be fairly, the first one is very frequently used, AUC, area under the receiver operating characteristic curve. And that's fairly common, tells us how the model does in general. And the other is what is the precision at just the top few % of users. And the reason we care about that is because those are the users that we're actually going to do something with. So the performance there is what we really, really care about. And lastly, we did have a baseline model, what I call the baseline model here, which is a previous solution that was built prior to our move to Spark. This model was built a while ago. It didn't take into account any of the new sites that had been generated, been around since then. So it's just something that we could compare against. So, all right, we have all of this information. What do we do first? What's the first reasonable thing to try? Well, maybe a linear dimensionality reduction. Maybe that will solve our problem. So what we could do is take our input which is our users, our sites, and our labels for each advertiser. And we basically run singular value decomposition on it. So very, very simple linear dimensionality reduction. And then we use the dimensionality reduced data to put into a classifier. So this is a stage where we have a classifier for every single advertiser because we have many different advertisers. So for this, I picked gradient boosted trees. And the reason for that is because they tend to work well out of the box, and they tend to perform well as well. We played around with different ones, but this one seems to typically do best. So, all right, great. How does this model perform? Let's take a look. So I have the two metrics up there, AUC and precision at the top 5%. You'll notice that they're box plot instead of individual points because, again, we have many different advertisers, therefore many different models. So you already see that there's already a lift from our baseline model, which is great news. Maybe we're already done here, and this this talk is over, but this talk is not over, so there has to be a catch here, right? What could possibly be the catch? Well, I mean, as data scientists, sometimes we need to look into our model and just make sure that they are doing what they're actually doing. So let's pick two of our advertisers and see what are some of the top sites that are associated with those advertisers. So here's one on the left. It's a home improvement advertiser, and another advertiser on the right that is in the telecom vertical. So what do we notice here? So, I mean, there's a lot of overlap between these two advertisers that have really very little to do with each other. I mean, why could this possibly be? I mean, none of the sites up there have anything to do with home improvement or telecom much. These aren't real sites, by the way, but they're just representations of what came up. So the reason is that the singular value decomposition actually picked out a common signal across all of these advertisers. So what they did was it identified online buyers in general, not those specific to each advertisers. So while the models did great, it was unfortunately not appropriate for our use case. So, all right, what do we do now? I mean, one common thing that you could suggest is, well, we did one singular value decomposition for everybody. Why not do a separate dimensionality reduction for each of our advertisers? So in this case, instead of doing dimensionality reduction on just a sample of users, make sure to add on the positive converters for each advertiser. And there are really two reasons why this did not work out. One of them has to do, again, with the scarcity of the positive samples. So most of the data used for each singular value decomposition is still going to be very similar to each other. And the other has to do with the computational costs associated with evaluating all of these different singular value decompositions and doing these dimensionality reduction steps this many times. So this was not a model that was computationally possible for us. So, well, what else can we do? We could try a nonlinear approach. We could use a nonlinear dimensionality reduction. And this is a perfectly valid way that we could have gone. And had we gone this way, what we would have to do is find a model that is both simple enough that we could run frequently so that new sites can be incorporated in a timely manner, and be expressive enough that we don't run into the same problem that we did with SVDs. But this is not what we did. What we did was this. We asked ourselves the question, can we simplify? I mean, what's the intuition behind what we're trying to do? It's really not that complicated. It's really just, if we know that somebody converted and they had gone to a particular site, we want to give credit to not just that site, but other similar sites, and target users who's been on these other sites as well. So one natural way to do this is to treat sites as a graph structure. So graphs are nice because they're fairly easy to interpret, easy to visualize, easy to see what's going on, and graph algorithms tends to be fairly well studied. So in our case, we're going to treat our sites as vertices, and then we're going to treat edges as connections between those sites, signifying some kind of similarity. So the sites can also have attributes, such as, in this case, I have the size of the vertex as the number of unique visitors, which we'll use later. And the edges, the edge weights, can be defined in several different ways. All of them pretty much has to do with the amount of visitors that are shared between the two vertices. So at this point, we started exploring GraphX, which is Spark's API for parallel graph computations. It comes with fairly common graph algorithms, and more importantly, it comes with APIs for developing new algorithms. Specifically, the one that we're going to look at today is Pregel. Pregel is a message passing API, and its model is think like a vertex. So what does that actually mean? Well, what it means is we define algorithms by specifying three things. The first is how a vertex sends messages to other vertices. Now, typically, vertices will send messages to other vertices through the edges. That's fairly natural. But there isn't really a limitation on that. But typically, you want to send them along the edges. The other is, the second is how messages gets merged together. So messages will be reduced together down to one final message. So these are messages that are going to the same end vertices. And the third is, given a merged message, how do we update the vertex data that the message is going to? And then this process can repeat as many times as it needs to. Each step here, each set of these three steps is called a superstep. There's synchronization between the steps, but there's no order guarantee on which order you're going to receive the messages. They're just going to be joined together in arbitrary orders. So how can we leverage Pregel to solve our problem? Well, here's the idea. The idea is to pass positive information, conversion information, along the edges so that we can give credit to similar sites. So remember our stick figure Bob from our first slide? Let's imagine that Bob actually is a converter for one of the advertisers that we're looking at, and he's been to that particular site. What we'll want to do is send that information along the edges to other sites that are similar to it. So let's go into the math, but let's go into the math using an example scenario. So let's pull this scenario, and what we're going to do is we're going to take each vertex. What we're going to do is initialize the vertex data with what we're going to call a weight. And that weight, at first, is going to just be the number of converters who's been on that vertex, that site, divide by the total number of unique visitors who's been on that site. So as you can imagine, this is going to be fairly sparse, lots of zeros, some ones, some non-zeros, and we're going to resolve that in just a bit. And the way we're going to do that is by allowing these vertices to send messages to other vertices. So what's our message going to be? Well, we want our message, shown here by delta omega, to be related to both the weight of the source vertex and the edge weight. We don't want to send the same message to everybody. We want the similarity of the two vertices to have some say in what the message is going to be. So our message is going to be the multiple of the two. So that's the delta omegas. And then what we're going to do is we're going to aggregate those messages together. So in this case, I've used simple summation to aggregate all of the messages going to a particular node. And the other step that comes after that is, well, how do we use this message, this combined message, to update our target vertex? And the way we're going to do that is we're going to take our old weight, so omega old, and then we're going to add a lambda multiple of the merged message. And then the sum of those two is going to be our new weights. And then after one iteration, this might be an example of what our weights might look like. And this can continue on for multiple iterations as long as we like. So here's some simplified code in Scala to tie everything together. So at the top, we have some type definitions for our message type, edge, and vertex data types. We have a couple of hyperparameters, and then the exact three functions that we talked about. And lastly, at the very bottom, a call to Pregel. So what we get out of that is a set of weights that go with each site. And this can be extracted out of the graph. And you can see on the right an example of what that might look like. It's really just a key value pair of sites to their weights, which is great because it's fairly small. To apply the model, we don't need GraphX at all. We just need to look at this. And the way that we might do that is, well, given a new user, let's look at all of the sites that we know they've been to. And then we'll look up the scores of those sites and aggregate that. The other nice thing about this that actually I forgot to mention is we are typically a Python shop. We did not touch Scala prior to this. And most of our model application pipeline is in Python. And the nice thing about this for us is we can evaluate this model in Python instead of having to go back to Scala to do this. So there are a couple of other factors that I didn't really get to. One is, well, how do we specifically define the edge weights? I've tested the three that's listed above, cosine similarity, Jaccard index, and conditional probability. And they're fairly, they performed fairly similarly, with conditional probability doing slightly better. So by conditional probability, what I mean is the probability that somebody in the receiving site also went to the sending site. So it's not the other way around. The other thing that we didn't really get into was the cleaning of the graph prior to doing the propagation. So we don't want vertices, we don't want sites that only one person had ever been to. So removing those tend to solve not removing those tend to introduce problems. And then there are our hyperparameters, tuning the lambda, tuning the number of iterations, and other parameters through testing. So there isn't really a notion of convergence here. So so the number of iterations is something that we needed to find by testing. There are also a couple of other not quite hyperparameters, but other options, like how do we aggregate certain things? Do we sum them? Do we average them? And those were tested as well. So, all right, how did we actually do? So it turns out that our performance is fairly similar to our SVDs, and it again beat our baseline, which is great, good enough for us. But this isn't the real test here. The real test is, does it actually give us good results? And in order to find that out, let's look at the 2 advertisers that we picked again, and see what sites are now associated with those advertisers. And here it is. So on the left, our home improvement advertiser. 3 of those are fairly relevant to renovations, home improvement, which is great. Others may be slightly related to the vertical that we typically target for that advertiser. And on the right, for the telecom advertiser, Canada, how did that get in there? Well, turns out that this telecom advertiser is a Canadian telecom. And so this is actually a fairly relevant signal that we're getting out of this. And also the other 2 that are down there are telecom related. So, woohoo, it works. So in addition to having reasonable performance and results, the propagation model also resolves the challenges that we talked about in fairly interesting ways. So for the site being numerous and being ever-changing, the dimensionality is, it's not really explicitly resolved, but we resolve that problem using the parallelism of GraphX. And this graph building process is fairly quick for us. It's maybe on the order of minutes, tens of minutes at most. So it is something that we could do as often as we like right before training our actual model, which means that we can take into account new sites every time we train the model, which is great. The other has to do with the second one here, having to build multiple models, one for each advertiser. And this is also fine because the graph itself is only built once. Only the propagation needs to run multiple times. And this is actually one of the parts where Scala's parallel data structure actually helped a lot for us, so that we can run multiple models at the same time. The third had to do with the sparsity of our positive training cases. And we resolved that in a fairly intuitive way, in a way that is easy to interpret. And the model output is, again, fairly easy to interpret. And lastly, the model running fairly frequently. We've resolved that by having an output that is fairly small and that does not require GraphX to run. And it's fairly fast to just look up those numbers and add them together. So before I conclude, there are several Spark learnings that I like to share with you. Some of them is maybe Scala specific, but most of them apply to both Python and Scala. The first is we found that when we tried to run large jobs, that tended to cause problems if we wanted to also run other jobs at the same time. One of the ways that we resolve that is by splitting that into smaller jobs. So as an example, instead of having one job that uses 200 cores, have 4 jobs that use 50 cores, tended to help improve throughput, be friendlier to other people who are also using the cluster. The second has to do with serialization. Serialization tends to be a pain pretty much anywhere. There are rules that may seem kind of arbitrary. So if you define a Python class, it needs to be in a separate file in order for that class to be serializable. Sometimes Spark may trick you into thinking that it's serialized and deserialized properly, but when you look into the object itself, your data isn't there. So know what can and cannot be serialized, and try not to save Spark context as a member variable. The third one up there, reduce by key versus group by key, that's a fairly easy one to understand. Group by key, you're grouping all of your data and then bringing that into memory, which is less efficient than using a reduce by key. And finally, just be careful with coalesce versus repartition. And partition by, it can be very helpful if you're running something fairly heavy the next step. So this is all I have for you. Thank you.
Hi.
Hi.
Thanks for your talk. I'm struck by the similarity between your solution and PageRank for search terms.
Yeah.
Do they share an underlying insight that would help to generalize to other solutions?
That's an interesting question. I mean, we did look at PageRank at first, and I think there is a lot of similarity if you look at the code. But there were also some differences as well. There was a really good reason why we didn't end up using it. I can't quite remember it at the moment, which is a terrible answer. But yeah, I think there's something there.
Thanks for the talk. My question is regarding the constant that you are using for calculating the weight. So how do you come up with some constant to increase the weight between the vertex? So,
yeah. So we just tested a few different variations and just figured out what worked best. So cross validation.
Okay, thanks.
Hi, thanks for the talk. I was curious, just simple question, how large the networks are per advertiser?
Yeah. So you mean how big the size of the graph is? So it's the same graph for every advertiser because the underlying graph structure doesn't really change. And it's maybe 1 million or so sites.
Thanks again for the talk. I was interested that the graph-based approach and the SVD linear classification approach seem to produce the same kind of results on your performance metrics.
Yep.
And the graph-based approach, based on what you were showing at the end, it feels good, like that feels right, that those sites are coming up for those advertisers. But if you think that that's producing a superior model, do you have any thoughts on why that wasn't reflected in the hard performance metrics?
Yeah, so I mean, there's a signal that I think that's fairly strong. That's basically, the signal that says you are an online buyer, you are an online buyer, you are an online buyer, right? And not really specific to each advertiser. And maybe there is a strong enough signal there that we could use that the other model, the graph-based model, isn't really leveraging. But at the end of the day, it's we're going to target these users, right? So we're going to do something with those users, and we don't really. It doesn't really make sense for us to target the same users for all of our advertisers. We kind of want different advertisers to target different users as well for internal competition reasons. So there's a business angle to this as well that the metric isn't really capturing, and you're right about that.
Thanks.
Hi, a related question. Did you try these models in live tests with your advertisers?
Yes, yes. So this model, we did take it live. The thing is, we don't just use this one model. The output of this model gets merged with the outputs of other models. At the end of the day, yes, it did work out for us.
But did it work better than your previous model
Yes.
and the SVD model?
We did not push that one to, we did not live test that one for that reason, that we didn't want everybody to be targeting the same group of users.
So thanks for. So for different advertisers that have similar graphs, did you consider training them together to strengthen the results?
Yeah, that's a good question. We did not, and part of it is it's an ethical reason where we didn't want to have data from two different advertisers sort of bleed into each other. It's really not fair for some advertisers that might have a bigger pool of users. So that's the reason.
Interesting talk. What's the meaning of the iterations? Do you have a new nodes add to it?
That's a good question. I don't know if this is the right interpretation, but my interpretation is the more you're iterating, the more you're kind of passing the messages to lesser nodes. So one interpretation is it's reducing the complexity of the model. By complexity, I mean in terms of the degree of freedom, because it's basically it sort of does an average out type of operation. So that's how I've interpreted it.
Have you had a chance to try, like if the number of iterations increase versus very few,
Yep.
Is there any significant difference?
So we found that fewer iterations tended to work well. So
Your attention, please. We are testing the fire alarm system. Please ignore all fire alarm speakers and strobes. You may
Are there any other questions?
elevators. Your attention, please. We're testing the fire alarm system.
Did you consider trying association modeling, a priori or karma, to try and find combinations that generated lift?
that's an interesting one. We didn't try that, no. Thank you. All right, thank you very much.